In this video, I want us to look at first order linear DEs, solving first order linear DEs. Yeah, let us start right away with the example. Yeah, so example 1, we are going to do several examples. I want you to stick with me such that you can get your exercise towards the end and you understand fully what first order linear DEs are, and you'll never forget them again. Let us say they have told us solve or find the general solution of, and then they give us a DE. So a DE is dy by dx plus 3y is equal to e of 2x. Now, to explain briefly what first order linear DEs are. First order linear DEs are those types of DE that obey or are in the order they obey or are in the order of dy by dx plus py is equal to q. Now, these are DEs that come from the exact DEs. They come from the exact DEs. But these ones, we have to use something called the integrating factor. And the integrating factor I is always E, the integral of P dx. Now, whenever we get the integrating factor, step 1, whenever you find a DE of this form, the first step you do is steps followed. Step number 1. 1. Get the integrating factor. Get the integrating factor. Step number 2. After getting the integrating factor, step number 2. Multiply the integrating factor throughout the DE. Multiply the integrating factor I throughout so multiply it throughout the DE. Now, the moment you multiply it throughout the DE, it has now turned into exact DE. It now turns into exact DE. Now, let us solve this. So now know that for you to get a DE of first order linear DE, it must be in the form of this, and 2, you must get the integrating factor. So now if you go to our equation 1, the example, so the example is, so let us for example get the solution. We get the solution. So our DE was dy by dx plus py is equal to q. That's the form. But now the DE is dy by dx and then plus 3y is equal to e over 2x. So we first identify the value of p. What is p from this one? So our p from here is 3. So therefore we go ahead to get the integrating factor. So getting the integrating factor I is going to be the exponential integral of 3 dx, which gives us I as e of 3x. Now, after getting 3x, we don't add plus c there, because of scientifically proven that you don't need to add c there. So after getting the integrating factor this, we have to multiply it throughout our DE. So therefore, multiplying it throughout our DE, we shall have e power 3x into dy by dx plus 3y is equal to e of 2x. So therefore expanding we shall have e of 3x dy by dx, then plus 3 e of 3x y, and then is equal to e of 3x times e of 3x. Now if we go ahead to simplify this, we shall have e of 3x dy by dx, then plus 3 e of 3x y is equal to e of 5x. Now this is what we said, that the moment we multiply throughout, this one is now exact DE. It has now turned into exact DE. Now I made a video about exact DE. If you haven't looked at it or watched it, I'm going to drop it in the description. You can go and watch it. It's very simple work. Now go ahead to solve this. So this exact goes back, so it ends up being that this is the same as y e of 3x then dx. So it came from this came from that, therefore is equal to e of 5x. Now we can go ahead and integrate on both sides. So we have the integral this side and also the integral this side. So simplifying, we shall have y e of 3x is equal to 1 out of 5. When you integrate e exponential power x, power 5x, you get 1 out of 5 e of 5x then plus sc. So this is our general solution. Now this first example, we are focusing on an exponential. Let us also look at another one where we focus on algebraic. So example 2, example 2, still solve the DE, and the DE is dy by dx, then plus 2xy is equal to x. Now you must identify, first of all, you must make sure that they resemble, it resembles the format acceptable. So the format acceptable says that you have to be dy by dx plus py is equal to q. Now can we get p? If true you can get p, and truly you can get p, you can truly get p. So our p is 2x. So if we can get p, we can get the integrating factor. So the integrating factor is going to be an exponential integral of 2x dx. So our I is e of x squared, like that. Now the next step is to multiply it throughout. So we shall have e of x squared multiplying throughout into dy by dx plus 2xy is equal to x. So expanding, when we expand, we shall have e x squared dy by dx plus 2xy e of x squared is equal to x e of x squared. So this one has turned into exact. So if it has turned into exact, we know that it comes from, now if you look at it keenly, it comes from y e of x squared dx is equal to x e of x squared. So we can go ahead and integrate both sides. When you integrate, this is very cheap work, very cheap work. When you integrate on both sides, you will have y e of x squared is equal to Now you go ahead to integrate this other side. So how do you integrate that side? I didn't want to drop it just right away. Let us do it in a procedural way. In a procedural way, we come and let our u equal to x squared. Differentiating this, you get du dx is equal to 2x. So therefore, we can say our dx is the same as du out of 2x. So you're going to substitute it back. So substituting it back, we have y e of x squared is equal to, put it back, we shall have x e of u times du out of 2x. So this cancels with that. So simplifying this, we end up having y e of x squared is equal to half e of u du. Integrating this and finishing it, we have y e of x squared is equal to half e of u plus c. And putting back our u, so we have y e of x squared is equal to half e of x squared plus c. As simple as this. Now, the moment you understand how to identify p, the rest becomes cheap work. The rest just becomes cheap work. Now, lastly, we have done the one for algebraic exponential. Now let us do one for trigonometric. So trigonometric, example 1. This is example 3. Please, if you haven't liked the video, like the video. If you haven't subscribed, please subscribe. Such that you understand. Now we have solve the dE. So we have dy by dx minus y tan of x is equal to x. So now what is our p from here? Comparing it with our general form, is equal to q. So we have our p as negative tan of x. Therefore, our integrating factor is going to be e negative integral of tan x dx. So which is the same as e of negative ln negative, actually negative, it becomes a positive. So ln of cos x. So which eventually becomes cos x. So therefore, multiplying it throughout, so we shall have our cos of x into dy by dx minus y tan of x is equal to cos of x. Multiplying it to the other side, it is multiplying into x. So therefore, simplifying this, we end up having cos of x dy by dx minus y sin of x, because cos times tan we get sin x, is equal to x cos x. So this one we said it becomes exact. this becomes exact. So when we finish it, this one is the same as it came from the derivative of y cos x dx is equivalent to x cos x. So we integrate both sides. So when we integrate both sides, we shall have y cos of x is equal to, now the other one is by parts. So this one goes for by parts, C. So we apply by parts. We use something called the eyelet, where we can come and say we have algebraic, we have trigonometric. So algebraic comes first, so our u becomes x, then our dv dx is cos x. So when you differentiate this, x, you get 1. So du dx is equal to 1, and then v, when you integrate that, you get sine of x. Now applying it back, so we shall have y cos of x is equal to, put in uv, it is x sine x minus the integral of v, which is sine x. So you have to be knowing the formula for by parts, times 1 times dx. So simplifying this, we shall have y cos of x is equal to x sine x sine x minus, so plus cos x plus c. As simple as this. So that is the solution. Yours to try solve the DE. Yours goes like this. Yours goes like this. Dy by dx plus 3xy is equal to e of 2x. I'm giving it to 2 dy by dx minus y plus y tan x is equal to x plus 1. As simple as that. Don't forget to follow. If you have understood, share it with your friend. We meet in the next one. We shall look at homogeneous DEs. Thank you so much. We'll meet in the next.